Rahul Alam from Memorial University of Newfoundland, from our host country. Please.
Thank you very much. You should not have told me about the time, because when I start talking, I don't stop. I'll try to stop today. Okay. So whoever knows me, perhaps you know that I love turbulence, and I talk about turbulence. So maybe I can say that next 20 minutes we pass through turbulence and first 10 years seatbelt. Okay, so here is just a quick acknowledgement of my research team and collaborators. So I'm a mathematician, also cross-appointed in physics, but I very much work with engineers and physicists. My main focus is on computational fluid dynamics of turbulent flow. Particularly, I look at wind farm simulation and large simulation, etc. Okay, so today I'll try to go over a little bit of a different side of wind energy, because I know this conference is basically looking at the technological side, but there is a physics side and science side of wind energy. There are a lot of issues that we do not understand, and if we understand those things, we can develop better technology. So I will highlight on that atmospheric science point, and then I will go briefly about scale adaptive large eddy simulation. Large eddy simulation technique is very much, I would say that my team, my students have developed, and we are now working on combining the LES with AI to have a digital twin. And we are looking at, for example, in Northwest Atlantic, if we plan to install wind energy, the main problem is that we don't have the real data. So if we can create a digital twin somehow, that we could utilize that to better understand this. Then I will discuss some results and some findings. Okay. So the first point is that the wind turbine size is even getting bigger than bigger airplane or Eiffel Tower, and we perhaps want to reach about 500 diameter. Currently, I think 240 diameter is very much standard for offshore wind. For this purpose, you also need maintenance and kind of how do you go there? A person should go, or a drone should go, or something. You need also look for offshore safety, and then flying helicopters, etc. So we are looking at large eddy simulation to understand this type of problems. Second challenge is that a wind turbine has 6 degrees of freedom of motion. So you want to design proper pitch control, and I have seen different sessions taught in different way. But one thing is wind turbines extract kinetic energy from the atmosphere. And in the atmosphere, when the wind passes to the half height, you can apply a proper pitch control technique to align your rotor to the wind direction. But because of the Earth's rotation, due to Ekman bear, the wind direction will gradually change and will rotate off of the direction about 30 to 45 degrees, depending on the region and depending on turbine. So, if wind generates wave, the wave direction and wind direction will not be aligned. When floating wind turbine was designed, very much it was designed based on the equation shown here, that wind and wave perhaps could be aligned, and then we can maximize the wind power. The last term here, 2/3 U bar AW square. That term indicates that if we have wind and wave are aligned, that wind energy can be enhanced. But if there is a misalignment, that could create fatigue. So the problem because of the Ekman spiral, we have misalignment, and we are trying to understand by large eddy simulation how we can incorporate those things into the design principles. The third challenge coming from atmospheric science is called entrainment, and often people tell me what is entertainment. So it is not entertainment, it's entrainment. So the entrainment is something, a fluid property that a fluid in the atmosphere from the upper level, fluid can, momentum can be transported downward to the ground level, and it's because of the boundary layer here. Okay. Now on the other side, you can see that because of the wind turbine, the boundary layer profile changes. So entrainment process changes. So if the entrainment goes to detrainment, that wind turbine's performance downgrade. If the entrainment is increased, that wind turbine, the wind turbine's the wake will produce more power. So as we know that on the first row, it gets the most of the energy. The second row, wake effect starts and wake effect starts. And we have different philosophy, different ideas, wake recovery. But one thing is entrainment. If there is an entrainment, then we can have a better wake recovery. And this is something, this equation is used by meteorologists, but how do we incorporate that? I think the most of the studies was done at Johns Hopkins by Charles Menew's group, but still it is in progress. How do we build a proper entrainment technique, incorporate these to the design principle?